Welcome everyone. I'm excited to kick off today's presentation on fire protection SYSTMS. We'll be exploring safety, detection, and suppression, key elements that keep our spaces secure. Over the next few slides, we'll look at how these systems work together to protect lives and property. Let's get started. Let's start by looking at the different types of fire extinguishers. We have AFFF foam, dry powder, CO₂, and water. Each of these is suitable for different types of fires and environments, so choosing the right one is crucial for effective firefighting. Now, moving on to the design formula for detector placement. The key idea here is that each smoke detector typically covers about 80 to 85 square meters, while heat detectors cover around 50 to 65 square meters. These are general coverage estimates and can vary depending on the specific product. To figure out how many detectors you need for a given area, you'll divide the total area by the coverage area of a single detector. For example, if your room is 22 meters by 12 meters, that's 264 square meters in total. Dividing 264 by the typical coverage of about 81 square meters for smoke detection gives you approximately 3.26. Since you can't have a fraction of a detector, you'd round up and use 4 smoke detectors for that space. Finally, the recommended spacing between detectors is around 9 meters for smoke detectors and about 7.5 meters for heat detectors. This spacing helps ensure comprehensive coverage and reliable detection. So, in practice, when designing a fire detection system, you'd calculate the total area, divide by the coverage per detector, and then install them with the appropriate spacing to maximize safety and effectiveness. Let's start with the clean agent fire suppression system. This system typically uses FM-200, Novec 1230, or Inergen as the extinguishing agents. These are effective, environmentally friendly options designed to quickly suppress fires without damaging sensitive equipment. The system detects fires using flame detectors, which are highly sensitive and capable of rapid detection, ensuring a swift response. This setup is particularly ideal for protecting sensitive equipment in data centers, server rooms, or areas with valuable electronics. Now, moving on to the voltage drop formula. Maintaining proper voltage is critical for system reliability. The formula V drop equals 2 times the length of the cable, multiplied by the current, and then multiplied by the cable's resistance per meter. Keeping at least 21 volts at the last device is essential, especially for a 24-volt NAC loop, to ensure proper operation. For example, if we have a cable length of 120 meters one way, a current of 1.4 amps, and a cable resistance of 0.009 ohms per meter, the voltage drop calculates to approximately 3.02 volts. Subtracting that from 24 volts, we get about 20.98 volts at the device, which is acceptable, so it's okay. Lastly, let's talk about battery sizing. To determine the right battery capacity, we use this formula. A equals the standby current times the standby time, plus the alarm current times the alarm time, all divided by 0.8 to account for efficiency. For example, if the standby current is 0.35 amps for 24 hours, and the alarm current is 1.8 amps for 0.083 hours, the calculation gives us around 8.55 Ah. Dividing by 0.8, we get approximately 10.7 Ah. So, in this case, choosing a 12 Ah battery at 24 volts provides a reliable backup. These calculations and system choices are vital for ensuring your fire protection system is both effective and dependable. Let's take a closer look at the fire protection concept. It mainly involves 2 systems: the fire alarm system, which is responsible for detection and notification, and the fire suppression system, which takes action to extinguish the fire. Both are critical for ensuring safety and minimizing damage. Now, focusing on the sprinkler flow formula, Q equals K times the square root of P here. Q represents the flow rate. K is a coefficient that depends on the system, and P is the pressure. For example, if K equals 80, then at 0.5 bar pressure, the flow rate Q is about 57 liters per minute. This helps us determine how much water the sprinkler can deliver under certain conditions. Moving on to hydraulic demand, we calculate the total flow rate, Q total, by multiplying the water density, ρ, by the remote area. For instance, if ρ is 2 liters per minute per square meter, and the area is 186 square meters, then the total flow rate becomes 372 liters per minute. This flow rate typically supplies around 7 sprinkler heads simultaneously. Finally, let's discuss pipe friction, which we often evaluate using the Hazen-Williams equation. The head loss, or pressure drop, depends on the pipe length L, the flow rate Q, the pipe's roughness coefficient C, and the diameter D. The formula is equals 10.67 times L times Q to the power of 1.852, divided by C to the power of 1.852 times D to the power of 4.871. Understanding this helps us design piping systems that maintain adequate pressure and flow for effective fire suppression. All these concepts are interconnected and essential for creating a reliable fire protection system that safeguards people and property effectively. Let's start by looking at the components of a fire alarm system. First, we have the detector, which is responsible for sensing smoke or heat. Then, there's the control panel, which acts as the brain of the system, processing signals from the detectors. Finally, we have the notification devices, like sirens and call points, which alert occupants to evacuate. Now, moving on to the mass formula, which is crucial for understanding how much fire suppression agent we need. The formula is M equals ρ mix times V room times C design times FD times F-leak. Here, M represents the mass of the agent required. Let's break down each component. Ρ mix is the density of the mixed agent, V room is the volume of the room, C design is the design concentration for effective suppression, FD accounts for temperature variations, and F-leak adjusts for potential leakage or system inefficiencies. For example, suppose we have a room measuring 8 by 5 by 3 meters. That gives us a volume of 120 cubic meters. If the design concentration is 5%, with a temperature factor of 1.1 and a leakage factor of 1.05, we can plug these into our formula. Calculating that, we find the required agent mass is approximately 6.93 cubic meters equivalent. Based on this, we would select the next larger cylinder set to ensure adequate coverage. This process highlights how important proper calculations are in designing an effective fire suppression system that aligns with safety standards. Let's take a closer look at fire alarm detectors. There are several types to consider: smoke detectors, heat detectors, flame detectors, and gas detectors. Each one is designed to sense specific signs of a fire, helping us respond quickly and effectively. Moving on, we also need to be aware of different suppression methods. For example, CO₂ flooding systems typically release between 34 and 65% volume per volume, depending on the hazard we're dealing with. This range is important because it ensures we have enough gas to suppress the fire without overpressurizing the space. In kitchen environments, fire suppression relies heavily on the hood system. The amount of agent used depends on the plenum volume and specific nozzle tables, which are designed to optimize coverage and safety. Lastly, aerosol suppression systems are another option. These systems release a measured amount of aerosol, calculated from vendor tables based on mass or volume. We usually add about 10% to account for potential leakage, ensuring the system remains effective even if some agent escapes. All of these detection and suppression methods tie back to our overall goal: protecting lives and property efficiently and reliably. Let's take a closer look at the foam and powder systems. When it comes to foam systems, the key components include the foam generator, the tank, and the nozzle. The foam generator is responsible for creating the foam mixture, which is then stored in the tank until needed. When a fire occurs, the foam is discharged through the nozzle, effectively smothering the flames and preventing reignition. On the other hand, dry powder extinguishers operate quite differently. They use a dry powder substance that is expelled through a discharge nozzle. The powder works by interrupting the chemical reaction of the fire, making it particularly effective for different types of fires, including electrical and flammable liquids. Connecting these points to our overall theme, both foam and powder systems are designed for rapid response and effective fire suppression, but they do so through different mechanisms tailored to specific fire types. Understanding these differences helps us choose the right system for each situation, ensuring safety and efficiency. Let's take a closer look at some of our specialty systems that play a crucial role in fire safety. First, we have kitchen hood suppression. This system is specifically designed to protect commercial kitchens by quickly detecting and suppressing fires that can start from cooking equipment. It's an essential safety feature because kitchen fires can spread rapidly and cause significant damage. Next, we have aerosol fire suppression systems. These are quite innovative because they use a fine aerosol mist to suppress fires. What's great about them is that they are effective in small, hard-to-reach spaces, and they leave no residue, making cleanup much easier. Both of these systems highlight the importance of tailored fire protection solutions. They connect to our overall theme of providing specialized, reliable safety measures for different environments. By integrating these advanced systems, we're ensuring that every unique space receives the precise protection it needs. Let's take a moment to summarize and compare the two main concepts we've discussed. First, the alarm system is all about detecting and warning. When a potential hazard is identified, the alarm alerts us so we can take appropriate action. It's essentially the system's way of saying, "Hey, something's going on here, pay attention." On the other hand, suppression is about acting and extinguishing. Once the alarm has alerted us to a problem, suppression kicks in to directly address the issue, whether that's putting out a fire or stopping a hazardous process. These two functions are closely connected, but serve different purposes. The alarm is the first line of defense, detection and warning, while suppression is the response that follows to resolve the situation. Understanding this distinction is key because it highlights the overall theme of safety and effective response. Detect early, warn clearly, then act decisively. This framework ensures we're proactive and prepared at every step. Thank you so much for your attention today. I really appreciate you being here and engaging with the material we've covered. Before we wrap up, I want to open the floor to any questions you might have. Please feel free to ask anything that's on your mind or clarify any points. Your feedback and curiosity are important, and I'm happy to discuss further. Again, thank you for your time and participation. It's been a pleasure sharing this information with you. So now, who has the first question?